Hello everyone. The topic of our presentation today is caustic simulation, making light patterns look real. We are
আবিদ হাসান খন্দকার
and Giant Testing, students from Department of Computer Science and Engineering at Bangladesh University of Engineering and Technology. Today we will be discussing the fascinating phenomenon of caustics and how we can simulate them in computer graphics. What exactly are caustics? Caustics are the beautiful bright patterns of light that you see on a surface. These patterns occur when light rays are bent or focused after hitting a shiny or transparent object, such as water or a glass. A classic example is the shimmering light patterns you see at the bottom of a swimming pool on a sunny day. Another example is the bright spot created by a magnifying glass. The diagram on this slide shows how parallel light rays are focused by a lens to create a caustic on a surface. Why are they so hard to render? Rendering caustic is a major challenge in computer graphics. The standard method of tracing light rays backwards from the camera is not effective for caustics. This method, which asks what color is the point on the wall, is like trying to finding a needle in a giant haystack when it comes to rendering caustic. For a camera disk ray to capture a caustic, it would have to magically hit a tiny specific spot on a glass object that would bend the light just right. This almost never happens, which results in a noisy image that lacks the beautiful light patterns we want to create. The smart solution, thinking like the light. The smart solution is to flip the problem and trace the light forward instead of backward. We use a technique called photon mapping, which is a two-step process. First, we simulate the light itself, then the second step. We use that information to create the final image from the camera's perspective. The diagram illustrates this two-step process, showing photons being traced from a light source through a glass object and a camera rendering the same in the second step. Step 1, the photon pass, building a light map. The first step in the photon mapping is the photon pass. We begin by imagining millions of tiny light particles or photons being emitted from a light source. We then follow each photon's path through the scene. Then, when a photon hits a shiny object like a glass, we can calculate how the light bends and continue tracing its path. Once the photon lands on the surface, like the floor, we record its exact location and brightness. The data is all stored in a light map or a photon map.
Step 2, rendering pass. The second step is rendering pass. The computer draws the scene from camera's point of view just like regular renderer. However, when it hits the surface, it doesn't just gauge the color. Instead, it refers to the light map that we created in the first step. It checks a small area around that point on the map to see how many photons have landed there. If the photons landed in that area is not much, in that case the area becomes dim, and if the number of photons is larger, then the area is bright. This is how beautiful caustic patterns are created in the final rendered image. We also tried to simulate this using codes, and these are some snippets of those code. Let me show you in practicals. Here is the code to simulate a swimming pool with three lights on top. Let's run the code. Uh, I know this image doesn't look actually realistic because caustic calculation are really heavy computationally, and we actually cannot exactly simulate that using our personal PC. If we little bit zoom in, then we can see at the bottom of the swimming pool, there are some caustic patterns. These patterns doesn't look exactly real because we used finite number of photons to simulate. Let me enable the photon to be visible. See, the photons are moving and sometimes they are uh, too many photons in one exact spot and those spots become brighter. I think you got the idea. And other ideas. The photon map is a key component and it is more than just a list. It is highly efficient data structure similar to a specialized tree that allows for very fast searching for nearby photons. We can also use Caustic map, which is a separate dedicated map only for the photons that create caustics to speed up the process even more. Another advanced technique is bidirectional path tracing, which attempts to meet light from both the camera and light source in the middle. Where do we see caustics in real life? Caustic simulation is used in many real-world applications. It is essential for creating lifelike water and glass effect in movies and high-end games. We see it in product advertising to make diamond rings and glassware look incredibly realistic. Architecture also uses this technology to simulate how sunlight will interact with a building's glass and water features before construction even begins. These images uh, in this slide show examples from video game architectural project and a movie called Blade Runner 2049. However, Caustic is not perfect. It has its own challenges and downsides. Despite its effectiveness, Caustic simulation with photon mapping has some challenges. The process is slow because simulating millions of photons requires a lot of time and processing power. It also uses a lot of memory to store all the data of the photon map. To achieve best results, there is often a lot of trial and error involved in guessing and checking settings, such as what number of photons is most suitable. Finally, the resulting image is an approximation, it's not a perfect physical simulation. To put in a nutshell, the caustics are beautiful but complex light phenomenon that standard rendering techniques cannot handle efficiently. Photon mapping provides a solution by tracing light from its sources and creating a map where the light goes. The technique is vital for creating the incredibly realistic images that we see in modern movies, games, and product designs. Thank you everyone for watching this video. I hope you enjoyed it.